In this section, we're mostly going to talk about how delta G relates to equilibrium, and we're going to end it by talking about coupled reactions and microstates, which is another way to think about entropy. So from the previous video, we know that the free energy for a reaction at standard states can be calculated using this equation. So then we can just look at the appendix in the back of a textbook or find particular numbers for the delta G of formation online. And if we know the chemical reaction, we can use the stoichiometry of that reaction, so the stoichiometry of the balanced chemical reaction, to figure out the delta G at standard state conditions. But most of the time, reactions are not at standard state conditions. They're in some other state, a different temperature, a different pressure, for example. So how can we find delta G for systems that are not at standard state conditions or that are not at equilibrium? Because we know delta G at equilibrium is 0. So we learned previously in equilibrium chapter that when Q is less than K, the reaction proceeds forward. When Q is greater than K, the reaction proceeds in reverse. If we take this and we compare it to delta G, we know that a spontaneous reaction is a reaction that proceeds in the forward direction, and in that case, delta G of the reaction is less than 0. So therefore, in this case, Q must be less than K. For reactions that are spontaneous in the reverse direction, we know that delta G of the reaction is greater than 0, therefore Q must be greater than K. So from this we can say that delta G of reaction depends both on the standard free energy, delta G naught, and on the concentration of reactants and products in the reaction mixture. So we can define the equation below: delta G at non-standard state conditions equals delta G at standard state conditions plus RT times the natural log of Q. At equilibrium, we know that Q equals K, right? The equilibrium constant equals the reaction quotient, and we also know that delta G equals 0. So from the equation shown on the previous slide, if we substitute delta G for 0 because the reaction's at equilibrium, we end up with another equation: delta G naught equals minus RT times the natural log of K, or if we rearrange it, we can solve for the equilibrium constant. So this equation is useful because sometimes it's very difficult to determine equilibrium constants just by measuring concentrations of reactants and products. If a reaction is very product favored, then there won't be very many reactants remaining, and it might be very difficult to measure concentrations of reactant. On the other hand, if a reaction is very reactant favored, then there will be very few products to measure concentrations of, and again, we may not be able to do that because the concentrations are so low. So instead, if we know the delta G at standard state conditions, we can calculate equilibrium constants using this equation rather than what we've learned in previous chapters. So if we look at this particular reaction, N2O4 in equilibrium with 2NO2, it has a standard state delta G of 4.8 kilojoules. So that means at standard state conditions, this reaction does not proceed in the forward direction. It would proceed spontaneously in the reverse direction. Now, if we compare this to our discussion previously on Q and K, remember when Q is less than K, the reaction proceeds to the right. That's when we only have reactants. So that's when we are right there on this curve, the first circle, condition 1. And the reaction always wants to go towards the minimum energy. So it's like rolling a ball down a hill. The reaction wants to go in the forward direction, so towards the right, to achieve equilibrium. Now, if we have only products up here in condition 2, Q is larger than K, and the reaction has to proceed to the left in order to reach equilibrium, right? So the reaction has to proceed this way, starting from condition 2. It has to proceed this way to the right, starting from condition 1. So on this graph, the reaction would want to proceed to the left in order to reach equilibrium. And if the reaction is at equilibrium, then we're at condition 3, where the reaction has already reached the minimum energy. So the reaction has nowhere to go. It can't go to the right and it can't go to the left. So let's relate this back to our equilibrium chapter. So if we have an equilibrium constant that is much greater than 1, we know that this reaction is product favored, so at equilibrium there will be more products than there are reactants. When we're talking about thermodynamics, that means that delta G is going to be less than 0. And if you remember these energy diagrams from previous chapters, remember that because the activation energy is smaller in the forward direction than it is in the reverse direction, that means that the reaction is going to be product favored. Okay, so again, at equilibrium, there will be a higher concentration of products than there are reactants. So if we had an equilibrium constant that was slightly greater than 1, so it is still going to be product favored. We're still going to have a delta G that is slightly negative or less than 0, but at equilibrium the reaction won't be highly product favored, it will only be slightly product favored. And again, if we look at the energy diagram, we can see that the activation energy for the forward reaction is just slightly larger than the activation energy for the reverse reaction. Now if we have an equilibrium constant that is much less than 1, that means the reaction is reactant favored. And if the reaction is reactant favored, then delta G naught is going to be greater than 0. A positive delta G means the reaction is spontaneous in the reverse direction. And from our energy diagram, we can see that the activation energy for the forward reaction is a lot greater than the activation energy for the reverse reaction. So the reverse reaction is going to be the spontaneous reaction in this case, and we're going to have more reactants than products at equilibrium. So let's just go through a quick calculation and determine the equilibrium constant and delta G of formation for this particular reaction. So the first step is going to be to determine the delta G at standard state conditions. And we know how to do that. We use this equation right here. And we're given the information, the delta G of formation for each of the reactants and products, so we can easily figure out what the delta G of reaction is at standard state conditions. So if we fill in the numbers, we end up getting a delta G of reaction at standard state conditions of minus 41 kilojoules per mole. Now the second part of the question asks us to find the equilibrium constant. So we can use the equation from a previous slide to calculate the equilibrium constant. And the thing to be aware of is that delta G, as we calculated, was in kilojoules per mole, but we need to have it in joules per mole in our equation. And the reason for that is the constant, 8.314, is also in joules. So make sure to make that conversion, otherwise you're not going to get the right answer. So solving for K, we end up getting 1.54 times 10 to the 7. So now let's quickly talk about the influence of temperature on the equilibrium constant. So we know at equilibrium, delta G naught equals minus RT times the natural log of the equilibrium constant. And we also know that delta G equals delta H minus T delta S. So we can make minus RT natural log K equal to delta H minus T delta S, do a little bit of rearrangement, and that gets us to a point where we have the equation of a straight line. So natural log of K is Y, minus delta H over Y is M, 1 over T is X, and the delta S over R is B. So if we were to plot the equilibrium constant versus the temperature, we would end up with a straight line where the slope is minus delta H over R, the intercept is delta S over R, and from this we could calculate or determine what the delta H of the reaction is and what the delta S of the reaction is. Now, another way we can determine what equilibrium constants are at different temperatures is to use the Van 't Hoff equation. So if we know the equilibrium constant at one temperature, we can find the equilibrium constant at another temperature. So notice that this is very similar to the Clausius-Clapeyron equation that you learned about previously. So let's just go through a quick example of the Van 't Hoff equation. So at 2000 degrees Celsius, the value of the equilibrium constant for this reaction is 4.1 times 10 to the minus 4. What is the value of K at 75 degrees Celsius if delta H equals 180.6 kilojoules? So we know we're going to use the Van 't Hoff equation. And now all we have to do is fill in the equation with the appropriate values. And again, since we are given kilojoules for delta H and our constant is in joules, we have to make sure that the delta H in the equation is given in joules. So the other thing to be aware of is to make sure that K1 and K2 are in the right part of the equation and T1 and T2 are in the right part of the equation. So the K value for K1 has to correspond to temperature 1 and equilibrium constant K2 has to correspond to T2. So now we can just solve for the right-hand side of the equation because all we have over there is a bunch of numbers and we end up getting what we see here. Now to get rid of the natural log, all we have to do is take the inverse natural log of both sides of the equation. So that cancels out the natural log on the left-hand side and we have e to the minus 52.86 on the right-hand side. All we have to do now is rearrange the equation, solve for K2, and we end up with a number of 4.51 times 10 to the minus 27. So now I want to talk a little bit about how delta G can be related to living systems. So in living systems, breaking down food or generating heat is a spontaneous process. So delta G for those reactions is negative or less than 0, so that's a spontaneous process. Whereas metabolic processes such as building muscle are not spontaneous. It takes energy in order for that to happen. So the process of life itself increases the entropy of the universe by converting chemical energy into heat. So we're going to talk about the breakdown of glucose. So this is something that you will learn a lot about if you move on and take biochemistry. So the process is called glycolysis, and it is the process of turning glucose, which is a sugar used by all living organisms for energy, into energy that the body can use. So we're going to look at the first part of glycolysis, where glucose turns into pyruvate. So just to give you an idea of what glycolysis looks like, this slide shows you the whole process, and the only part we're going to be looking at is the part that's circled. So the first part of glycolysis is called the phosphorylation reaction, and that results in the addition of a phosphate group to an organic molecule. So the phosphate group is the one that is circled in red, and it is added to the glucose molecule. Now this particular process has a delta G of reaction of 13.8 kilojoules per mole. So that is a non-spontaneous process because delta G of the reaction is greater than 0. So if this process has to occur in order for glucose to produce energy for the organism, how does this process proceed? I'm sure many, if not all of you, have heard of ATP or adenosine triphosphate, and that is the energy storage system of living organisms. So it's produced as a result of breaking down or metabolizing food, and it can be used to drive non-spontaneous processes to make them spontaneous. So this is the structure of ATP, and you can notice it has 3 phosphate groups. And in the process of phosphorylation, one of those phosphate groups is added to glucose, and that results in the ATP, adenosine triphosphate, turning into ADP, or adenosine diphosphate. And this process, ATP going to ADP, is a spontaneous process. It has a negative delta G value of minus 30.5 kilojoules per mole. So by coupling these two reactions together, what nature is able to do is to take non-spontaneous processes and turn them into spontaneous processes. So I'm going to end this section and talk about entropy and microstates. So microstates is just another way to think about entropy. So I'm going to start off by talking about molecular motion. So the motion of molecules is what is called quantized. And that just means that there are only very specific states of energy that molecules can exist in. So it's kind of like the volume control on your phone. You can turn your phone to volumes of 1, 2, 3, 4, 5, but you can't turn it to 4.5, 6.6, 2.4, for example. So there's only very specific levels of volume that your phone can be set to, and there are only specific energy levels that are allowed in a molecule. And a microstate is a unique distribution of particles among these energy levels. And that is what is meant when we talk about something being quantized. It has very specific energy levels that are allowed. So remember, there are 3 types of motion: translational, rotational, and vibrational. And as temperature increases, the amount of motion from translational, rotational, and vibrational motion increases. So you have more vibration at higher temperatures, more rotation, and more translation. So another way to look at quantized energy states is to think of it as this kind of upside down graph, where there are specific vibrational states of oxygen that are allowed. So we're looking at an O2 molecule, and it's vibrating in such a way that sometimes it's so far apart, other times it's closer together, and at other times it's farther apart. So that vibration of the molecule going in and out, those bonds getting longer and shorter. There are only specific energy levels or specific distances that those molecules can be apart. And that is represented by each of these lines. So we have quantized vibrational states represented by the red lines. And in between each of those red lines are quantized rotational states, which are represented by these blue lines. So the oxygen molecule can only exist on one of these lines. So it can exist with that particular energy, it can exist with this particular energy, but it can't exist with an energy somewhere in the middle there. So this graph is showing the energy with respect to how close each of the O atoms are with respect to each other. So when they're really close together, so the distance being 0, so they're basically touching, then we have a very, very large energy associated with that. When they're far apart, we also have a very large energy associated with that. And the molecule is going to be most happy when the energy level is somewhere down here. So when we're talking about microstates, we're talking about the distribution of different orientations of the molecules in a given space. So the number of microstates is given by n to the power of x, where n is the possible positions, x is the number of molecules, and the distribution with the largest number of microstates is the most probable distribution of molecules. So when we open up this valve, the most probable distribution of molecules is going to be what's shown over here. It's very improbable that the molecules will all be on one side of that particular vessel. So let's just demonstrate this using a smaller number of molecules or particles so you can see how this works. So let's just start with this particular situation where we have 4 particles, each different color, so we can see where they go. Now what's going to happen when we open up the valve? Well, a number of things can happen. They can stay in the left-hand side, they can go to the right-hand side. Okay, so there are 2 possible microstates where the molecules are on either side of that vessel. Now, if we have a situation where there is 3 molecules on one side and 1 molecule on the other, now we have 4 possible microstates that satisfy that particular condition. So it's more probable that we have 3 molecules on one side and 1 on the other than it is to have 4 molecules on one side and 0 on the other side. Now if we take that to the next step, where we have 2 molecules on either side, now we have 6 possible microstates where we have an equal number of molecules on each side of that vessel. So in this particular case, the most probable orientation of the molecules is where there are the most number of microstates, so where we have 2 molecules on either side of that vessel. Now, if we wanted to calculate the number of microstates in a particular system, we would use the Boltzmann equation. S is the entropy, W is the number of microstates, and K is the Boltzmann constant, being 1.3 times 10 to the minus 23 joules per Kelvin. So this equation indicates that the entropy increases as the number of microstates increases, and that makes sense. We have more microstates, we probably have more molecules, more energy levels at which they can exist, so that's going to result in more microstates or greater entropy. So that's all I have for this section. Let me know if you have any questions.